Let's take a few minutes here and look at reaction mechanisms. Now, reaction mechanisms are the step-by-step way that a reaction gets from the reactants to the products. And studying those really does tell us a lot about how the chemistry actually goes. So we're going to look at these and we're going to say, well, one of the things is we're going to find out that most of the steps, the step-by-step way things go, usually involve two molecules, and so we say they're bimolecular. They could be unimolecular, could be termolecular, but usually it's bimolecular. You can put the steps of a mechanism together to get the overall reaction. Some of the things that cancel out might be either reactive intermediates or they might be catalysts, and we want to be able to recognize those. The steps themselves, the slowest step is called the rate determining step, and we'll look at that. And then the big thing here is how can we relate that rate law to the rate determining step. And that's very, very important. It gives us big clues into which one mechanism might be better than another mechanism. Finally, we want to go back and look at a different type of mechanism called the chain reaction mechanism, and those are very important. So, from our worksheet, we have this idea that a chemical reaction depends on particles colliding into each other, and that's important. And so a really simple one might just be this particle AA bumps into another thing, BB, and then it turns into two ABs. So if I were to write this, I'd say AA plus BB turns into two ABs. This could be like hydrogen plus iodine turns into hydrogen iodide. Now, in order for this reactants to turn to products, okay, it first forms, some kind of a activated complex, a very unstable, high-energy molecule like that. And that relates back to our ideas about the potential energy diagram, that, the top of the hill, the top of that energy barrier, is the formation of this activated complex. This steps at which they're going together could be called the mechanism. Now let's look at another one, and this is fairly well understood. And this is 4 HBRs plus an O2 turn into 2 H2Os and a Br2. Well, the idea is if we're talking about 5 particles, 4 of these and 1 of those, have to collide into each other at the right place at the right time, okay, with enough energy to react and the right orientation, the idea that that could actually happen is so small, the probability that they're going to hit each other is so small that the rate for this reaction would be incredibly, incredibly slow. Okay, but we could kind of see we would get a couple of HBRs and a couple of H2Os and 2 Br2s. So for them to be in the same place at the same time with the correct orientation and with enough energy, it's just not going to happen. So people think this really does happen like in 3 steps. So one idea is that the HBr bumps into an O2. Okay, so we'd have an O2 and an HBr. So if these bump into each other with enough energy and the right orientation, then maybe the new bond would form here and a new bond would form here, and we'd keep one of these bonds and we would get a molecule that would be HOOBr. So we can call that a Huber, just for fun. Now, if we have this HOOBr, that could bump into another HBr, and we could see what would happen. So let's say we have H and a Br. Okay, well the bond that we had here could break, and maybe the other bond would break, and we could get a new bond here and a new bond here. So this is getting pretty messy looking, but you can kind of see that we would get 2 molecules that we could call Hober. Finally, a HOBr molecule could bump into an HBr molecule. And when that happened, so I'll put an H here and a Br here, and like before, okay, this bond here would break and we'd form some new bonds. So we'd have a bond here, we'd have a bond here, and we would get a Br2 and a H2O. Now we have two of these HOBRs, so this whole thing can happen twice. And if we do, we have another HBr. And when the bonds form, we could get a water molecule here and a Br2. So the idea is that this last step, even though it's two molecules bumping into each other, it could happen twice. So we have two HOBRs plus two HBRs turn into two H2Os and two Br2s. So this would be our reaction mechanism. Now, when we look at this, we say, well, I want to get my overall reaction. So we basically, kind of algebraically say everything on the left side of the equation turns into everything on the right side of the equation. And you can see that there would be chemicals that we could cancel. And what we're left with is 1, 2, 3, 4 HBRs and an O2. And we have two H2Os and two Br2s. So we get our overall reaction by combining these elementary steps. Now we're going to come back later and notice that for this first, this mechanism, that the first step here will probably be the slow step. Okay. Now molecules that are formed in one step and used up in a later step, those are called reactive intermediates. So for instance, in our reaction we just saw, the HOOBr, that was a reactive intermediate because it was formed in one step and used up in a later step. And the HOBRs were also reactive intermediates formed in one step and used up in a later step. Now we'll take another example here. The following mechanism is proposed. Write the equation for the overall reaction. So you can see we want to look at everything on the left and right. And what could we cancel? Well, we could see, pick a new color, that these F's could cancel, and that looks like everything. So what's our overall reaction? Well, looks like we have two NO2s, and we have an F2, and it turns into two NO2F, and that's it. Now we're balanced. Okay, so that's our overall reaction. And these little guys here, the F's in this case, those would be reactive intermediates. Now, these elementary steps are often involving two molecules at a time, and like we say, that would be called bimolecular. But you will see cases where maybe just one molecule just decomposes as one of the steps, and that would be unimolecular. Or maybe three molecules bump into each other, and that would be termolecular. So again, here's another reaction. Let's write the overall reaction. So what can we cancel? So we look at both sides. This IO minus, that would cancel. And you can see also this I minus, that would cancel. So write the overall reaction. What do we have left? So we have two H2O2s. Turn into two H2Os and an O2. Okay, where have we seen this reaction? We've seen this one several different times now. We've seen this when we were doing the micromole rockets. That was our generator for oxygen. We saw it when we did the elephant toothpaste demonstration, and we actually just saw this today in our class when we did the genie in the bottle reaction. But if you just put peroxide on a cut, this is what happens. And you might have seen it in biology where you use potato or liver, things like that. Now, we have two things that we canceled out. So we might say, okay, so IO3 minus, okay, that's a reactive intermediate. And I minus, that's a reactive intermediate. But I wouldn't really call this one a reactive intermediate. Okay, I would say that that is a catalyst. Okay, and so how can you recognize a catalyst in a mechanism? It does cross out, okay, just like our reactive intermediate crossed out, but in this case here, this molecule was used up and then it was regenerated in a later step. So it was used and then formed, let's say reformed, and that's what a catalyst does. whereas the reactive intermediate, okay, it was formed, okay, and then it was used up again later. So it was formed in between, but it got used up again, broken up. That's an intermediate. And if it is used and then reformed at the end, that's a catalyst. Because we said a catalyst somehow speeds up the reaction, but doesn't get used up in the reaction because it's regenerated in the last step. Now, in every mechanism, there is one step that is the slowest of all the different steps. So the reaction can only be as fast as this slowest step, and this is called the rate determining step, because this step determines the rate. So it's the rate determining step. Now, when we were looking at those mechanisms before, the first one we started with, then we said, well, HBr plus O2 turned into HOOBr, and I just happen to know that that is the slowest step in that mechanism. And we're going to come back and look at this for a moment. For a reaction, for any of the problems, they almost always tell you which step is fast and slow. Being able to come up with which is fast and slow, that takes a lot of experience and maybe some more information. Not something that would be normally asked on an AP test. So it says in the mechanism to the left, what was in the left column of our worksheet, the first step is a slow step, so I've copied it again here. If we want to speed up the reaction, we've got to speed up this step. And we can see what happens is that if we were to double the concentration of HBr, then the chances of an HBr bumping into an O2 would be doubled, and so therefore that would double the rate. So if we doubled the concentration of HBr, the rate would double. And hopefully you kind of realize, well, that's what we meant by first order. A first order reaction is one where you double the concentration and the rate doubles. And this is the reason. In the same way, for the O2, if we were to double its concentration, then that would double the chance that these two particles are going to collide. So it would also double this one. So we can see that the rate law is that we have K, concentration of HBr raised to some power, and concentration of O2 raised to some power. And from this information right here, we can see that that power is 1 and 1. So the rate law for the whole reaction is actually the rate law for the slowest step. So how does the rate law relate to the reaction mechanism? Is the rate law tells us about the slowest step. If we're coming up with a rate law where this is first order and this is first order, then that means the coefficients of this chemical and this chemical in the rate determining step are 1 and 1. Now, we said a long time ago that the rate law has nothing to do, these numbers here have nothing to do with the overall reaction. Okay, could be the overall reaction, but it doesn't have to be. And that's because it really has to do with the slowest step. And the slowest step, you can't tell what step is slowest from the overall reaction. So the rate law gives us a great way to test out one mechanism versus another mechanism and say this is a good mechanism, this is not a good mechanism. So let's practice a little bit. Okay, consider this mechanism, and we've seen this one a moment ago. Okay, write the equation for the overall reaction. So we say all we have to do is cross those two out, those are our intermediates. And so it's 2NO2 plus F2 turns into 2NO2F. Write the rate law for this reaction. Well, because we know, because we've labeled this one as a slow step, and there's one NO and one NO2 and one F2, then we know the rate law for this is going to be K NO2 to the first power F2 to the first power. So this is the rate law for this reaction because the orders here, 1 and 1, match the coefficients in the slow step. Now, another little piece about this is, we found the activated complex, we found the potential energy diagram for this reaction. And those two steps, we can see the first step, you have to go all the way up here. And then the second step, it's a little bit lower hill. Then overall, this is exothermic reaction. So how can you tell from this potential energy diagram that the first step is a slow step? Well, it's pretty easy. You can see that this has a bigger barrier. This has a larger activation energy. And so it's going to be fewer particles are going to be able to get over this taller barrier than are going to get over the second barrier. So this first step is going to be the slow step. Okay, next question. If here's a reaction and it follows this mechanism, first step is slow. Write the rate law. Again, if we want to write the rate law, then we're going to go by the slow step. There's one A, there's one B2, so the rate law is K, A to the first order, B2 also to the first order. And that's our rate law right there. So the rate law matches the slowest step in a mechanism. Now this bottom here, we're saying, let's say that these steps here, that these are the slow step in a mechanism. So we're saying here's a slow step, here's what the rate law would look like. Let's do the same thing with a bunch of different possibilities. So molecularity, say this would be a unimolecular, these would be bimolecular, these would be termolecular. And the rate law, okay, rate equals K. In this case, it would just be A to the first power. Since there's only one A, then it's going to be one chemical first order. Change colors. This one would be rate equals K. And we have two A's, so this would be A squared. Now the reason is, if two particles here have to collide, if we were to double the concentration of A, then that would double the chance that this particle in the collision is correct, and it would also double the chance that this particle is correct. So it would quadruple the chance that we make a good collision, and that's what happens with second order, is that if you double the concentration, that would quadruple the rate, and this rate law shows why it would happen. Okay, third one here. Let's say we have A plus B turns into products. So we'd say the rate is equal to K, concentration of A to the first power, B to the first power. So this reaction would be first order with respect to A, first order with respect to B, second order overall. For the fourth one down here, A plus A plus A, we have A, that's our only chemical, and this would be to the third power. So if we were to double this concentration, it would be double times double times double, and that would be 8 times increase in the rate. If we had A and 2B, okay, it would be concentration K, it would be A to the first power, it would be B squared, third order overall. And our last one would be the rate equals K times A times B and times C. All to the first order, it would be a third order overall. So if your molecularity is 3, then we're going to end up with a third order overall rate law. If it's 2, then it's going to be second order overall. And again, if the molecularity is 1, then it's going to be first order overall. Now the other question here, this comes from an old AP question, and we see what happens here. Write the balanced equation for the overall reaction. So let's go through and knock off anything that shows up on both sides. And so the overall reaction here would be O3 plus O turns into 2 O2s. Now who's a catalyst? The catalyst is chlorine because it is used in an earlier step and then it's regenerated in a later step. It's used up in an early step and regenerated in a later step. And if this were my actual AP question, I'd be using complete sentence here. Now the other part, what about an intermediate? Well, the chlorine, ClO, that's our intermediate. And in this case, it's the ClO because it is formed in one step, but it is used up again in a later step. So it's formed and then used up. So the catalyst is used and then reformed, and the intermediate is formed and then used up. Another question from this: if the rate law for the overall reaction is found to be rate equals K O3 to the first order Cl to the first order, figure out what's the overall order of the reaction, and obviously the overall order is going to be 2. What are the appropriate units for the rate constant? Okay, we just solve for K. So K is equal to rate over a concentration times a concentration. So that would be something like moles per liter per second divided by moles per liter squared, so moles squared per liter squared. And we can see what's going to happen. One of our moles and liters is going to cancel, so our final answer would be liters moles to the -1 seconds to the -1. And you can make just as good an argument for saying that is minutes or hours. Okay, the last thing, the rate determining step. What is the rate determining step? Well, we look back at our reaction and say, okay, which one of these is slow? If this is the rate law, that's our clue. Okay, and the clue is there's an O3 and there's a Cl. Both of those have to appear in our step, and since they're both first order, there should be one O3 and one Cl. So we're looking for a step where there's an O3 plus a Cl turns into something else, and so obviously that's our first step here. So we know that the first step is the rate determining step. So determine which one is the rate determining step, so we'd say it's step 1. And the reason is that if it were step 2, we can eliminate that because our rate law would say ClO and O, and neither of those are in there. So it is step 1 because it has O3 to the first power, has one O3 and one Cl, which is going to give us, that's the rate law of the slow step, step 1. Okay, I want to take a few moments and just look at one last situation. And way in the beginning, we saw this picture where we said an A2 molecule plus a B2 molecule, okay, could turn into two ABs. And so possibly that could happen in one big step where these just collide into each other in the right thing, in the right orientation with enough energy so they can form the activated complex and then turn into the products. But there are some reactions that kind of follow this pattern. For instance, hydrogen plus iodine or hydrogen plus chlorine, and they find out that they actually run by a different mechanism. What happens is some light comes in and hits, let's say it hits the hydrogen, or it could hit the iodine, and breaks that molecule up. So instead of having, let's say, an H molecule that looks like that, Lewis dot structure, we get two separate H's, and we have a name for those where they come off with their own one single electron. We call those the free radicals. So this in our symbol here, A would be a free radical, and B over here with a dot. So the thing with the dot, those are free radicals, very reactive because that single electron is not stable to be by itself. It wants to find a pair. So the first step here where this would break up, and maybe that happens because of some light, so we'll say H nu, that's called the initiation step. Then what happens is one of those A's can bond with a B. So here's the A, can bond with a B2 molecule. So it would pull the B away from the other B and form AB. And then the B would be left with its single electron. So the A would be able to pair up with a B to make AB, but that would leave B with an unpaired electron. Then, as a second step, that B, which is very reactive, might bump into another A2, And so it would disrupt this bond. It would share an electron with one of the A's, form another AB, and when that happened, it would leave an A left over, A dot. So that's a free radical version of A. But the important part of this is if you look at these two steps, the A can now go back and tear apart another B2, and then the B can tear up another A2, and they can repeat these two steps back and forth and back and forth and back and forth. So maybe just starting with one of these molecules here might go through and interact with maybe 10,000 B2s and A2s to form tons and tons of AB. So that's called the propagation step. So we initiate the reaction, and this is called the chain reaction. We get the propagation means it just keeps going and going and going until two particles, and so maybe it could be an A dot with another A dot. Okay, it could turn into an A2, or maybe a B dot turns into a B2, or what I wrote here, an A and a B turn into AB. But two free radicals bump into each other and turn into a stable molecule. That's called the termination step. So a chain reaction has an initiation, a propagation, and then a termination step. So I just wanted to tell you about that type of reaction. So this is everything we have about chain reaction mechanisms.